spanning sets and linearly independent sets in both at the same time, because we're going to be talking about bases today again. So remember that when we're talking about a basis for a vector space, we're talking about a non-empty subset of the vector space. There's actually one exception to that, but it's a very, very minor exception to that. Talking about a non-empty subset of the vector space that is both linearly independent and spans. So remember, the reason why we want both of the conditions is because the spanning part tells you that you can write everything in terms of the basis elements. The linearly independent part tells you that you can do it uniquely, right? So there's one and only one way to express every vector in the vector space as a linear combination of the vectors in the basis. Again, we talked about just some standard ones that we've talked about, and we'll go back to the standard ones later on as well. But remember, in R3, if your vector space is R3 and your set is 1, 0, 0, 0, 1, 0, and 0, 0, 1, if I have a vector A, B, C in R3, how can I write it in terms of those three vectors? What would you do? So I need a specific constant. So if I have a vector ABC, what specific constants would you use to write that ABC in terms of the basis vectors? Yeah, A times the first, and B times the second, and C times the third, right? That's exactly how we would do it, right? That gives us a linear combination of the basis vectors that will give us the vector that we're interested in. And again, that's the only way to do it. That's the idea behind the basis, right? There's one and only one. Doesn't matter what the vector is, I can do it. And then once I've done it, that's the only way to do it. Again, if you've done Calc 3 or do physics, you probably call these, bless you, call these I, J, K, right? So you have A times I plus B times J plus C times K. Another way to do that. Again, the reason why we can do it that way is because the I, J, K, those three vectors form a basis for R3. Again, we had our standard way for checking if something is linearly independent or it spans is to do what? We have a set of vectors. What was our standard way of showing that it was linearly independent or it spanned? Yeah, make it a matrix. How do you form the matrix? Yeah, make each vector as a column, right? And then what do we do? Row reduce. And then if it spans, what do you see? Pivot in every row. If it's linearly independent, we see pivot in every column. Good. Okay, cool. All right, so let's see if we can apply that to this particular set. We're claiming is a basis for P3. Remember, P3 again is set of polynomials of degree 3 or less, and then including the zero polynomial, since the zero polynomial doesn't have a degree. All right, so again, the idea behind this is that we want to try to form a matrix and row reduce. So pardon me. The idea behind this, of course, is that I want to look at linear combinations of elements in the set and then see if we can form a matrix and row reduce. So if we look at a linear combination, there should be a comma here as opposed to a period. It was just a typo. A linear combination of things in the set would look like A times 1, B times 1 plus X, C times 1 plus X squared, and then D times 1 plus X squared plus X cubed. That's what a linear combination would look like of elements in the basis, right? Constant times the first, constant times the second, constant times the third, so on. We want to try to show that it's linearly independent and spans, and it's the same process every time, right? We want to try to form a matrix and row reduce, okay? So it doesn't really matter what's on the right-hand side. If it's equal to 0, that means I'm trying to show that it's linearly independent. If it equals some arbitrary polynomial, then I'm trying to show that it spans. So we want to do it the same way, correct? If we start gathering like terms, then if I can rewrite this particular sum on the left-hand side, if I combine like terms, your constant term looks like a plus b plus c plus d, right? Correct? Okay. Your x, what's the coefficient on the x term then? We have b plus c plus d on the x squared. Yeah, c plus d, and then the only thing on the x cubed term is the d, right? Again, if I'm trying to show that this is equal to some arbitrary polynomial or equal to the zero polynomial, I would need to equate coefficients, right? So this would be what the coefficient, the constant term would have to be the same. The coefficient on the x term would have to be the same. Coefficient on the x squared term, coefficient on the x cubed term, right? Those all have to be the same on both sides of the equation, right? So let's say we set it equal to 0 for argument's sake. It's the same argument if we were doing an arbitrary polynomial on the right-hand side. If this is going to be a true statement, then what has to be true about each of the coefficients here? Well, I'm just saying if I have a true statement about polynomials, what has to be true about each of the coefficients? What are they going to have to equal? They have to be zeros, right? So if this is going to be true, then we would need a plus b plus c plus d equal to 0, right? That would be one thing we would need. What else would we need? And a b plus c plus d equals 0. C plus d equals 0. D equals 0, right? We would have to have all of those things. If we had some arbitrary polynomial on the right-hand side, then this would have to be whatever the constant term is. This would have to be whatever the coefficient on the x term is, and so on down the line. But notice the left-hand side would be exactly the same, correct? Okay. When we want to, now this is not hard to solve, but because I can look at it and tell what the answers have to be. But if you were to try to solve this using a matrix, I'm trying to solve for the A, the B, the C, and the D, right? If we make a matrix out of that, your coefficient matrix would look like what? What would your coefficient matrix look like? It would be 1, 1, 1, 1 across the first row, right? Second row would be 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, right? And then it doesn't matter if it had zeros on the right-hand side or some other constants on the right-hand side we're trying to solve for. I'm going to row reduce exactly the same way, correct? Now, we think about when we've done this for vectors in R3, we said we form the matrix by just making the vectors and sticking them in columns, correct? Does that look like a parallel notion here that we just did with these polynomials? If I think about this is the constant, the x squared, the x cubed coefficient, isn't that exactly what we have for the first one? And then the second one, and the third one, and the fourth one. So this is going to, this is going to extend to other typical vector spaces that we deal with. We can still form our matrix by taking the coefficients here and putting them down the columns and row reducing. This is a special case of something we're going to talk about later on in a section of probably next week. It's the same kind of idea. If I row reduce this, are you going to see a pivot in every row and a pivot in every column? Are you going to see the identity matrix when you're done? Yeah. It's already upper triangular with ones down the diagonal, right? So if you were to row reduce this, I would kill this one by working off of this one. I would kill these two by working off of this one. I would kill these three by working off of that one. And we get the identity matrix. So we really do see that this is a basis. So if you, this one's pretty easy to see looking at it. But again, if you put it in your calculator and row reduce, you will see the identity matrix. So that shows that it's a basis. It's linearly independent because it has a pivot in every column. It spans because there's a pivot in every row. That make sense? All right. We've already mentioned this. I have this on the next page. We already proved it, I think, the other day anyway, as far as part of it. But again, the idea here is that this is why we care about bases. There's one and only one way to express any vector in the vector space as a linear combination of the v's. So the reason behind this, again, is because if S is a basis for V, then S, we're going to remember we say spans V. And again, the idea behind spanning means that for any vector in V, there exist constants C1, C2, out to Cn, such that W can be written as the C1V1 plus C2V2 CnVn. That's what spanning means, right? If a set spans a vector space, then we can write every single vector in the vector space as a linear combination of those basis vectors. Now again, this is an abstract notion, but the reason why we're doing it more abstractly is because we want to be able to apply this in various situations. And one of the ones I like to go to, of course, you've noticed this semester, is talk about differential equations. Is when you're talking about trying to solve a differential equation, you look for particular solutions. Well, I shouldn't say particular solutions. You look for solutions that generate an entire set of things. Right? Okay. One of the examples I think I've given you before is that if you look at the differential equation, you take the second derivative of the function and add the function again, you get 0. There are two kind of basic functions that do that. What function do you? Tell me one function that you know that the second derivative of that function is the negative of itself. Sine, and what else? Cosine, right? So I know that sine and cosine satisfy this differential equation, right? I also notice that this particular differential equation has second order, which means that there are it's second order and linear. From some theory from differential equations, that tells me that there are exactly 2 linearly independent solutions to this equation. So since I found the 2 of them that are linearly independent, which we could also check, then I know that all of the solutions have to be a linear combination of these 2 things, and that's all of them that there are, right? I know that every single solution to this differential equation has to look like this. These 2 generate all of them. That's one of the reasons why we try to do this more generally, because it has these applications. All right. In any event, what I'm saying here is that the solution space to this equation is spanned by these 2 things. Okay? So that's all we're saying as far as span goes. All right. So this was the existence part of the proof. There is at least one way to write W as a linear combination. We use span. The other property of the set, the basis we haven't used yet, is linear independence. The linear independence is where the uniqueness part comes in. So how do we typically prove uniqueness in math? What do we do? We want to show something is unique. What do we typically do? Yeah, assume there's 2 and show that they're the same, right? So we've already established 1. So now let's suppose, and this is the same proof we did the other day. Suppose that d1v1 plus d2v2 plus dnvn is also equal to W. We use the span to get the existence. So we typically in math, if you're stating a theorem, you don't assume more than you need, right? You're going to use everything you're given. somewhere. I haven't used linear independence yet, so to get the uniqueness part, I'm probably going to use linear independence. Definition of linear independence talks about linear combinations that give you what? What's the vector that has to be on the right-hand side if you're talking about linear independence? 0, right? You're looking at linear combinations that give you the 0 vector. If it's linearly independent, what's the only linear combination that gives you the 0 vector? What do you use for the constants? All zeros, right? Okay. So I need to somehow get a linear combination of the v's that give me the 0 vector. I now have 2 linear combinations that give me the same thing. How can I get something that involves the 0 vector? What do I need to do? So how do I get it equal to the 0 vector? If I use these 2 things that give me the same vector. Yeah, just subtract them from each other, right? Subtract the first equation and the second equation, right? If I subtract, we get C1 minus D1 V1 and a C2 minus D2 V2, bless you. A Cn minus Dn Vn is equal to the 0 vector, right? If we subtract those two. I now have a linear combination of the v's that gives me the 0 vector. So what does that tell me about all your constants? They're 0, good. So since S is linearly independent, we have that our C1 minus D1 is 0, C2 minus D2 is 0, Cn minus Dn is 0, right? Or we rearrange, what does that tell us about the C's and the D's? They're equal to each other, right? So C1 equals D1, C2 equals D2, Cn equals Dn. So did we really have 2 different linear combinations that gave us W, or did we have the exact same linear combination that just gave us W as twice? Same, good. Yeah, we have the same exact linear combination. So there's only one linear combination that gives us W. So what this allows you to do is do things like express things as coordinate vectors, which you do when you write ordered pairs in the plane, or ordered triples in space, right? Or write a vector in terms of I, J, and K. You work with coordinates. So this is why we care about uniqueness. It allows us to coordinatize vector spaces and express things in terms of coordinates. If I can express things in terms of coordinates, then I can really just deal with them in real numbers, or the real vector, like RNs. You treat them like they're RNs. That's the whole goal of this exercise. So anyway, this is why we care about bases. This is the important part, that I'm able to write everything uniquely. All right. So let's talk about the next example that I have on here. First part we've already talked about. How am I going to show that that set is a basis? What are we going to do? Yeah, make a matrix and row reduce it, right? How am I going to make my matrix? What am I going to do? Yeah, vectors as columns, right? We're going to take our vectors as columns and row reduce. So first column will be 5, 2, negative 7. Second column will be 4, negative 1, 3. Third column will be negative 3, 1, 8. We'll put that in reduced row echelon form. I'm betting it's going to reduce to be what? The identity matrix, right? It better. It says show that it is a basis. It didn't say determine whether or not it is, right? Okay. So it's probably going to row reduce to the identity matrix, and we'll show that in a second, but I'll just assume that that's what's going to happen. Remember, the reason why we want to see the identity matrix is because I need both qualities, right, of the set. I need it to span, so we need a pivot in every row. I want it to be linearly independent, so I need a pivot in every column. So I better see the identity matrix to see both at the same time. Okay? That makes sense? All right. If it is a basis, then I know that I can express any vector in my vector space. So for part B, in particular, I'm talking about this particular vector, right? If it is a basis, I can express this vector as a linear combination of those three, right? So I'm looking for, when we're talking about finding coordinates, I'm looking for the constants A, B, and C, in this case, since I know I have three vectors in my basis. We're looking for the constants A, B, and C that give us that vector. That's what we're looking for, right? The coordinates then of this vector will be your A, B, C. That's what we're looking for. How do you think we're going to find those? What do you think we're going to do? What do you think we're going to do? Yeah, put a matrix in, right? Notice that we need first components to match, so we would have to have 5a plus 4b minus 3c equal 24. That'd be one equation, right? What's another equation that you'd have to have? So if we equated the first equations as the first components together, you give 5a, 4b minus 3c. What would be another equation you would get? Yeah, 2a minus b plus c is 13, right? And then likewise for the third components, right? You see that system of equations that we would have, right? Notice that your coefficient on the A is the components of the first vector. The coefficients on the B will be the components of the second vector, and so on. So you're going to end up trying to solve the system where you've got your vectors going down columns, and your vector that you're interested in finding the coordinates for will be on the right-hand side of your equation. So again, we're making a matrix by forming the matrix as columns using the vectors, right? So if we want to row reduce this, calculator is handy. I'm going to do it in R because I can type it in faster in R than I can on the calculator, especially on the computer, if it finds the keyboard. Ooh. Oh, you know there's a keyboard there. Okay. Go back over to R here. So I need to make sure that I put in, I want to row reduce it. So, oops, misspelled the word library. Okay. Let's make your matrix by columns. So the first column was the 5, 2, negative 7. The second column was 4, negative 1, 3. Third column was 3, negative 3, 1, 8. And if you could tell me the last one, I'd appreciate it. Negative 67, like that? Okay, cool, thank you. All right. Remember the cbind command in R will form the matrix by taking those vectors and making them columns, right? You can do it in your calculator as well. I'm just doing it in R because it's a little faster to type in. Put it in reduced row echelon form and scroll it up so you can actually see. Here's a notice again, if I ignore the last column, we see the identity matrix there, so that would check that it's a basis. That's the part that would check that it's a basis, right? This tells me that A is 6, B is negative 3, C is negative 2. So those are your coordinates relative to that basis. 6, negative 3, negative 2 are the coordinates. Okay. So typically the way we write that, if I go back over here, I say 6, negative 3, negative 2. Thank you. Scroll. No, don't move that. So at 1, 0, 0, 6, 0, 1, 0, 1, 0, negative 3, 0. 0, 0, 1, negative 2. That's what we got when we're row reduced, right? So the way we typically write the notation that we'll use for coordinates relative to a basis, you take your vector, whatever the vector happens to be, put a little subscript to tell what basis you're talking about, and then write it as 6, negative 3, negative 2. So put the vector in parentheses. Doesn't matter if it's like an R3 vector, an Rn vector, it could be a polynomial, it could be a matrix. Put it in parentheses, put the subscript to talk about what basis you're talking about, and then write the coordinates like you would a vector in Rn. The idea, again, behind coordinatizing this is to treat every vector in a finite dimensional vector space. We haven't talked about what those words mean necessarily yet. But it's to treat every vector like it could be a vector in Rn. And then you can just analyze it like you would a vector in Rn, which we know how to do. Because those are the ones we're comfortable with. Any questions on how we came up with the matrix and what we did there? There. So I'll take that as a no. All right. There are standard bases to many vector spaces that we're already interested in. So one of them you're already familiar with is R3. Can you tell me 3 vectors that you can write every single vector as a linear combination of in R3? An easy one? We already wrote it down earlier today. Yeah, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? That would be your standard basis for R3. Because again, if you've got an ordered triple A, B, C, I can use A times the first, B times the second, C times the third, right? Those are the coordinates with respect to that basis. Can you extend this to Rn? Can you guess what the standard basis for Rn would be? Yep.
0, 1.
Yep. And then continue on to. Good. Yeah, exactly right? Put a 1 in the first component, put zeros everywhere else. Second one, put a 1 in the second component, put zeros everywhere else, and keep doing that until you run out of components. A simpler notation for this, and this is why we don't typically use E for vectors, a letter to use as a vector. EI is it's not an I, it's a 1. We use E sub I to represent the vector that has a 1 in the ith component and zeros everywhere else. That's why we don't typically use E for a vector notation, because we save it for this. So we could write this as E1, E2 out to En would be your standard basis. All right. How about P2? Remember, what's P2 again? Yeah, polynomials of degree 2 or less, right? How do you typically write an arbitrary polynomial of degree 2? You usually use an ax squared plus bx plus c, right? Agree with them? Okay. So what might you use to generate an ax squared, a bx, and a c? What basic pieces do you think you would use to generate an ax squared, a bx, and a c? What I mean by that is, remember up here we're trying to generate an ABC, right? So we use that for the A, that for the B, that for the C. So what might you use to generate every polynomial? So I'm not sure I want to use ordered period. I want to try to think about the polynomials that will generate it. Because I need to generate an x squared term, I need to generate an x term, I need to generate a constant term. What basic pieces do you think you might use to generate an x squared, an x, and a constant term?
An x plus something, an x plus something else.
Don't have to work that hard. Well, how do we generate the vector ABC for R3? What did we use? Why do we use 1, 0, 0? What does it generate? The A, right? Why do we use 0, 1, 0? The B. Why do we use 0, 0, 1? The C. Okay, again, I want to generate an AX squared, a BX, and a C. So what things might you use to try to generate an X squared term, an X term, and a constant? Yeah, an X squared, an X, and a constant, right? I would use those three pieces. So I could do this as, and usually we write it in the reverse order for the standard basis. I could use a 1. That'll generate all the constants, right? I can use an x. That'll generate all the x terms. And an x squared. That'll generate all the x squared terms. And then I can do linear combinations of those, and that'll give me every single polynomial, right? Because I would write a plus bx plus cx squared is a times 1 plus b times x plus c times x squared. Can you extend that to polynomials of degree n or less? What do you think you would use here? Yeah, we would need an x to the n to get the x to the n term. We would need an x to the n minus 1, an x to the n minus 2, and so on, right? Now, usually when we're at the standard basis, we usually order it the other way. So we need a constant term, an x term, an x squared term, and all the way up to an x to the nth term, right? Agreed? All right, so notice that in R3, we needed 3 things to generate, right? I had to generate the first component, second component, third component. Rn is just an extension of that. In P2, I need to generate 3 things as well, right? Then I generate a constant, an x and an x squared term. Or starting counting with 0, it's a degree 0 term, a degree 1 term, a degree 2 term, right? How many things are you going to have to generate if you're dealing with 2 by 3 matrices? How many things are you going to have to generate? 6, right? I got to generate the 1, 1 entry, the 1, 2 entry, the 1, 3 entry, 2, 1, 2, 2, 2, 3 entry, right? So this one's going to have 6 elements, should have 6 elements in a basis. What do they look like? Do you think? What do you think you would use to generate the 1, 1 entry? A 1. And where do you want everywhere else? Zeros, yeah. Right? Use a 1 and zeros everywhere else. How are you going to generate the 1, 2 entry? Yeah, do 0, 1, 0, 0, 0, 0. How are we going to generate the 1, 3 entry? 0, 0, 1, 0, 0, 0. And then keep going. Right? By the way, does that look any different than trying to generate a standard basis for R6? No, I just have it written as 2 rows as opposed to 1 single row. Looks exactly the same. How do you think, I'm not going to write it out, but how do you think you would do it for Mn? How many different, if you had M by N matrices, how many matrices are going to be in your basis? M times N, right? Because I've got to put a 1 in every single entry and zeros everywhere else to get the standard basis, right? So you would have M times N matrices that look like these. And notice it matches that 2 times 3, right? All right. Questions on the standard ones? All right. So let's do a couple of definitions here. I mentioned the word is finite dimensional when I was talking about our example with the differential equation. It's not a big definition. So notice that every single thing that we've written as far as the standard matrix, standard basis for the vector spaces that we have, all of them have a finite number of elements in the basis. That's all we mean by finite dimensional. So a vector space is finite dimensional if it has a finite basis. So if a basis for V has finitely many elements. So it doesn't say that the vector space has finitely many elements. It just says a basis has finitely many elements, right? R3 is a finite dimensional vector space because there's 3 elements in a basis. But there's infinitely many vectors in R3. So what do you think infinite dimensional means? Yeah, it is. Yeah, it's a basis has infinitely many elements, right? So if a basis has infinitely many elements. That's all infinite dimensional means. Examples of infinite dimensional vector spaces. Those function spaces we talked about, like continuous functions on an interval or differentiable functions on an interval, those are infinite dimensional vector spaces. However, there are subspaces that are finite dimensional. So this differential equation is talking about trying to find a subspace of twice differentiable functions. And so this is the subspace this is the subspace of the solution space for that. That solution space would have dimension 2 because there's 2 elements of the basis. Even though it's a piece of an infinite dimensional vector space. All we mean by finite dimensional is there's a finite number of elements in the space or in the basis for the space. Pardon me. That's all we mean. And all we're going to deal with are finite dimensional vector spaces. We want our bases to be finite. All right. So the next theorem talks about, or the next pieces of the theorem. Well, there's 2 pieces to the theorem. The next theorem talks about what has to be true about a basis. And let's think about it in terms of how we've checked other sets for whether or not they're a basis or not. Remember, to be a base, it has to be linearly independent and it has to span. And our main technique for checking that was what again? Yeah, put a vectors in the column as row readers, right? If it's going to be linearly independent, it has to have a pivot in every column, and if it's going to span, it's every row, right? So if it's going to do both at the same time, what has to be true about your matrix? What as far as the dimensions go for your matrix, what it has to be true? To be square, right? If I have one set bigger than the other, can it possibly be square if we do that? No. So what would this say here? If I'm trying to make a matrix out of this one, if M is bigger than N, if the M is bigger than the N, what has to be true when you make your matrix? Are you going to have more columns or more rows? There'd be columns, right? I'm going to end up with, this is a basis, right? So there's N here. I'm going to have more columns because this set's bigger, right? If I have more columns than I have rows, what happens? What are you going to get when you row reduce? Can you get a pivot in every column? If you have more columns than rows? No. So can it be linearly independent then? No, the set's too big, right? The next one down says if your M is smaller, then you're going to have more rows than columns. Can it span if you have more rows than columns? No. Okay. That's the idea behind doing vectors in Rn. Now, of course, we want to do this more generally. So let's do part A here. Probably all we have time for anyway. Let's do part A here. All right. So if I want to show that the T set here is linearly dependent. The idea behind showing that something is linearly dependent is that I want to create a homogeneous system that has more variables than equations. Because if we have a homogeneous system that has more variables than equations, we know we're always going to get free variables, so we get infinitely many solutions. So we can't have a unique linear combination that gives us the zero vector. All right. So let's talk about how we create that. Since the V1, V2 out to Vn, is a basis. By the way, I've got a typo here. These vectors up here really should be W's. I don't want them to make them in terms of I don't want them to be necessarily the same ones that are over here. So I should have W1, W2 out to Wm here. All right. Since I know I have a basis, I know a basis spans. I can write then everything in this subset, the W's, in terms of the V's, right? So I know there's a linear combination of the V's that give me W1. So I'll use the constants C11, C12, and so on down the line. Do the same thing for W2. Oops, V2. Write it as a linear combination of the V's. Keep doing this all the way down to the W's. I know it's subscript hell. All right, so all we're saying is that we have a basis. I know bases span the vector space, so every single vector in the vector space can be written as a linear combination of the V's. Okay? I want to show that the W set is linearly dependent. To show that it's linearly dependent, I need to talk about a linear combination of the W's that gives me the zero vector, but I didn't use all zeros for the constants. That's what linear dependence means. Okay? So if we suppose that let's say we have K1W1 plus K2W2 out to KMWM is equal to the zero vector. I want to start with a linear combination that gives me the zero vector. Well, if I look at this, I can rearrange things. If I do K1W1 plus K2W2 and all the way down to KMWM, I can rearrange, these equations here. I can collect my V1 terms, collect my V2 terms, and so on down the line. We would get what? C11K1 plus C21K2 plus CM1KM V1. And then likewise, going down the V2 column, I would have C12K1, C22K2, all the way down to CM2KM V2. And then do the last terms all the way out. So again, all we did was just run the K's through and then rearrange. Again, what are we assuming about the set of V's? We're assuming that it is a basis, right? Bases have two important characteristics. They span and they're linear independent. We already used span. So what do you think we're going to use next? Not a big surprise, right? We'll use linear independence. What do I have? It's long, but what do I have here? I have a linear combination of the V's that gives me the zero vector. If I have a set that's linearly independent, if I have a set of a linear combination that gives me the zero vector, what has to be true about all the constants? If it's linearly independent and I have a linear combination that gives me the zero vector, what has to be true about the constants? They're a zero, right? And I told you before we needed to set up a homogeneous system, right? So since our set is linearly independent, we have, and I'm running out of room here, that's okay, C11, K1, C21, K2, CM1, KM equals 0. Likewise for the second vector, the second constant on the second vector, second coefficient, whatever word I'm trying to use. I'll just make it up as I go along until I hit the right word that I want. I have a linear combination of these that gives me the zero vector, so all of the coefficients have to be 0. What kind of a linear system do we have now? I've got 0 constants on the right-hand side. What kind of system do we have? Homogeneous. How many equations? Yes. 1, 2, 3, up to n equations. How many variables are we trying to solve for? M of them. Which one was bigger, n or m? M was, right? The m was bigger than the n is what we're assuming, right? So do we have more equations or more variables? We have more variables, which means there are how many solutions? Infinitely many, right? This is a homogeneous system with more variables than equations. Whoops. So it has infinitely many solutions. Now remember, what are the variables here? What variables were we trying to solve for? Well, the variables of which constants though? Which variables? What letters are we trying to solve for? The C's we know we had because of the span. The thing we're trying to solve for is the K's, right? So this linear combination here is since we have infinitely many solutions, how many ways can we write the zero vector as a linear combination of the W's? How many solutions do we have here? Infinitely many. So how many ways can we write this linear combination? Infinitely many. That makes it linearly dependent, right? So that set T is dependent. Oops. All right, so what this does, and we'll finish this off on Monday. What this does is tell you how large a linearly independent set can get in a vector space. Once I have a basis, that's the cap on how large a linearly independent set can get. So a basis is a maximal linearly independent set. It's as big as you can get for linear independence. The second part talks about spanning, right? It says if it's too small, it can't span anymore. So a basis is also a minimal spanning set. It's maximal in terms of linearly independent, and it's minimal in terms of span. Since we didn't get through all this today, you can move your homework due date to Wednesday. All right. Have a good one. Enjoy the longer weekend again, because we have another day off. Keep getting days off.